Okay, let's start. Hey everyone, this is Charlie. I'm the co-founder and the principal of XCamp. Today we have the 2023-2024 season zero level live solution for this December contest. We are happy to have Max here. He's the ICPC, it's the college contest of the computing algorithms world finalist. Also, you may know XCamp. We are located in Silicon Valley. We provide coding classes for the students, especially on the competitive coding. Okay, great. So we are happy to have Max here. Max, how about you have an introduction about yourself?
Yep. Thank you, Charlie. So yeah, I'm Max, one of the instructors for XCamp. And yeah, also my credentials have already been stated by Charlie. But yeah, I'll be presenting today's solutions.
Okay, thank you. I will stop my screen sharing and turn the stage to Max.
Yep. So let's just go ahead and jump straight into talking about the problems. I'll just go ahead and do the explanations here on the whiteboard. So starting with the first problem. So the first problem was about towers and cows with weights. Yeah. So let's see. So we are given n we're given n distinct weights. So n is up to 2 times 10 to the 5, where we basically have we're given like things like pairs wi and ai both less than or equal to 10 to the 9, which means we have this means we have ai cows with weight wi. That's what this means. And so now we want to place them all into towers. So we have a total of m less than or equal to 10 to the 9 towers. And what we want to do is and we have some parameter k also less than 10 to the 9. And we are allowed to place basically we are allowed to place cows in the same tower as long as no two cows differ by no two cows differ by less than k. So an example is, let's say I have a tower of, so I can build towers like this. I can have a tower of cows. Suppose k is equal to 1, then I can build a tower with weights 3, 4, and 5. So this would be valid because any two cows differ by at least 1. I can build something that's like 2, 4, 6, 7, 9. This would also be a valid tower. But now let me give an example where, let's say k is equal to 3. Then a valid tower will be 3, 6, 9, 12. This will be a valid tower. But an invalid tower would be 3, 6, 8, and 12, because 6 and 8 only differ by 2. So this will be an invalid tower. And then, of course, I can't have like two equal weights. Like something like 3 and 3 is blatantly not allowed, since that would be difference of 0. Okay, so we got the definition of towers out of the way. So now what we want to do is, using the fact that we have at most m towers, we want to place the cows, try to place as many cows into towers as possible. So we want to maximize the number of cows used in towers. We don't need to maximize the number of towers we use or anything like that, or total weight or anything like that. We just need to maximize the number of cows that are used in towers. So how can we approach this problem? Well, there's a lot of parameters kind of flying around, and it might be a little daunting at first to just like try to attack this problem head on. So we can try to reason about this in some sort of, let's say, a greedy sense, because when constraints are large, typically a greedy solution is like one of the only type of solution that is feasible. So let's say we consider building some towers. Let's consider the first the minimum weight cow. So consider the minimum weight. Well, then, from a greedy perspective, it would make sense to try to use as many of these minimum weight cows in towers as possible, right? Let's say I want to place them as like a bunch of, suppose the minimum weight is 2, then maybe I want to start by creating a bunch of towers, that all have 2. Um, and it would make sense for me to put these cows in towers with weight 2, because suppose I don't use one of these cows and I instead like save it for a cow that's going to have weight 3. then that's only going to decrease my number of options in the future, right? Because a tower that has 2 on top versus a tower that has 3 on top, the tower with 2 on top has more options. If k was, because for 2, I can put anything starting from 2 plus k, 3 plus k, 4 plus k, so on and so forth. But for 3, I can only start placing from 3 plus k, 4 plus k, and so on. And so from a greedy perspective, I want to minimize the tops of these towers, right? So that's the first bit of greedy intuition we might have. And so this kind of motivates us to maybe start looking at this from maybe sort the cows and consider them from smallest weight to largest weight. So let's try doing something like that. Let's try sorting by weight. So we're going to sort by weight. We're going to have a bunch of towers. Initially, let's say we have a bunch of towers. Let's say they initially all have negative infinity at the top. So the idea is that these towers are going to be built from I guess bottom to top, and the weights are going to keep getting larger. Initially they all have negative infinity because you can place anything on top of them. There is no restriction. And now let's say we have let's say our total list is we have 2 cows of weight 2, 3 cows of weight 3, 1 cow of weight 5, 1 cow of weight 8, 1 cow of weight 9, 1 cow of weight 11, something like this, right? So we have a bunch of different weights. And let's say k was equal to, let's say k is equal to 2 in this problem. So if I'm processing all of my weight, first I consider the cows of weight 2, right? I consider these 2s. And I can choose to put the 2 on top of some towers. So maybe I put them on top of here. So now these towers have cows of weight 2 on top of them. So this would already increase my answer by 2 plus 2 because I used 2 cows. Now, something that might come to mind is, do we want to use all these cows? Maybe we choose not to use one of these cows. We choose to not use it. But if you think about it for a bit, it doesn't make sense to not use a cow, because whether you choose to put like this cow with weight 2 or put some other cow with weight 3 later on, both of these contribute just plus 1 to the answer. So it's like if you choose to give up this cow spot to get a cow later, that's plus 1 either way to the answer. And if we're going to take like a cow no matter what, we want to take the cow as the smallest because that creates the most number of options in the future, right? Like having a 2 on top, it gives more options than having a 3 on top. And so from a greedy perspective, we always want to use the 2s. We always want to use a cow whenever we can. So let's go ahead and use both these cows. Both of these have 2. Now we move on to weight 3. 3 is going to have not enough. Actually, for the sake of example, I'm going to add 1 more cow of weight 3 just to showcase this. So for 3, I want to place all these cows if I can, but I only have 5 towers. I can't place them on top of here, but I'll place them on top of here. And now you can see I've used 3 cows. I've contributed plus 3 to my answer. Unfortunately, I have nowhere I can place this 4th cow, so we're just going to skip over it. Now let's move to 5. So for 5, we can choose to place we can place we can place the 5. We can place it here, or we can place it here. And I guess if you look at this, from a greedy perspective, it makes more sense to place it on here because this minimizes the overall set of cows that we have, right? This makes it a 2, 2, 3, 3, 5, whereas this one makes it like 2, 3, 3, 3, 5. So instead of a 2, we have a 3. Now, so therefore, you could say that it is greedily optimal to place it on top of 5. But interestingly enough, for this problem, it actually does not matter which one you place it on. We can actually place it on the 2. And the way you can prove this is, suppose that you're placing it on the 3 because you want to save the 2 for something else. Well, then that something else can also be placed on top of the 3 because that something else is going to be greater than 5. So it's also going to have distance at least plus 2 from 3. So actually here, it is okay for us to put the 5 on top of the 2 or on top of the 3. Let's just place it on top of the 2 for now. And I make this distinction because it's going to make the implementation of the algorithm much easier later. So let's say I place the 5 here. So I place the 5 here. Now the 5 is done. Now I'll move on to 8. I'm going to place it, let's say I place the 8 here. Also move on. The 9, I place it here. Move on. 11, I'm going to place him here. Move on. And then 12, finally, I place it here, move on. So here I have placed all but 1 cow, which is a pretty optimal answer. is the best we can possibly do for this test case. So what exactly have I described here? Let's actually outline a concrete algorithm now. So here's the idea. I'm going to have a minimum priority queue. So a priority queue that brings the minimum to the top. And I don't want to have like 10 to the 9 different towers inside a priority queue. That's too much memory. I'm going to compress it. I'm going to store pairs. And I'm going to store pairs of representing the tower. It's going to be the weight on top of the tower and the number of towers I have of this with this weight. So it's compressed form, basically. I'm going to store this priority queue. Initially, it's just going to have one pair of negative infinity with m of these. And then what I'm going to do is I'm going to go through each of the distinct weights one by one. And what I'm going to do is keep hopping from this priority queue and add cows until like two things happen. Either one, the PQ is empty, or two, the top of the PQs, the minimum weight, top of PQ plus K is now greater than the current weight we're trying to place. So we can no longer place this weight cow anymore. I already see there's maybe a few questions. I'll get to that in a second. Yeah, but let me finish the explanation first. So yeah, basically I want to keep adding cows. I'm basically just going to greedily add cows by popping out the priority queue and adding it to the topmost. Yeah, adding it to the smallest weight each time. And then at the end, I just need to add. At the end, I can just add like one like weight. Let's say weight WI with the new count. And so what is the complexity of this? Well, the complexity of this is that each time there are kind of like two cases. Each time we processing for priority queue, either it's removed forever, or it is or we ran out of the cow, which can only happen at most once. So the total amount of work we do is bounded by, we'll say, order n log n. Because each pair is added, there are only at most O of n pairs that can be generated, and each pair is added at most once and removed at most once from this priority queue. And the proof of correctness of this algorithm is what I described above. So you always want to use a cow whenever you can. And yeah, you always want to use a cow whenever you can. And there is no reason to, like, you always want to keep it as minimal as possible. And then finally, basically it doesn't when you have like a tie between different towers and get added to, it actually does not matter. So in our algorithm with the priority queue, we're always going to be adding it to the smallest weight tower, or that's the weight tower with the smallest weight on top. All right, so that summarizes this problem. I'm gonna go ahead and take a look at the chat now, see if I'm gonna take a look at the chat now. All right, starting with the first one. Should two pointers also work? Actually, yeah, now that I look at it, for this part, you don't actually need a priority queue because the priority queue is always going to be like, you're always going to be adding something with the largest weight to the priority queue, like larger than anything else so far, and it'll always be removed from the smallest one. So actually, you are correct that we could substitute this priority queue for some sort of two pointers instead, where basically you have like one pointer for where you start for the next tower to add to, next tower to add, and then you have one pointer here, and then you have one pointer for like the current weight. And then both of these will always move forward. And so that would actually reduce this part of the algorithm down to O of n. Although the overall algorithm is still n log n because you still have to sort. So the sort still makes it n log n. But it is true that we could use a two pointers for the second part and save it and like make that part like a little slightly more efficient. Yeah. Let me see if there are any other algorithms. Or sorry, let me see if there are any other questions. Yeah, was time complexity, so that'll be, yeah, as I stated. And and log n, because I think you have to do a sort regardless. Yeah. And someone's asking about problem 3 now, so we will cover that. We will cover that soon. All right, any other questions on problem 1?